All right, lesson number 2 in this module, we're going to talk about describing how APs initialize, get their initial configuration, what the discovery process is. We talked about that a little bit already, the basic discovery process, but now we need to get into some of the details, because I will say this, that a lot of times when you're doing a new deployment, or not usually when you're adding gear, but when you're doing a new deployment, one of the things that you run into quite a bit is the inability to get the APs to actually recognize the controller and join the actual network. So that's what this lesson is all about, understanding that process, how the process occurs, how do I identify if there's going to be a particular issue with this process, and so on. So we'll take a look at how APs discover the controllers, what the failover process is, how we can establish failover priorities. We'll take a look at high availability, and then we'll also take a look at other modes of operation, and just really in-depth looked at this initialization process. All right. So the initial discovery process, really the whole goal of that process is to allow the access points to discover as many controllers that they can see as possible, which will then allow for that redundancy, right? Without, if I can't connect to the primary controller, I want to be able to connect to a secondary controller, or even maybe, and this is another component that you can configure, if I have redundant controllers, maybe I want to just connect to the least loaded controller, right? The controller that doesn't have as many APs and as much responsibility. So the lightweight AP, and we talked about this in our previous lesson, can learn the management IP address of the controller through several different methods. Actually, there's 4 different methods that we can learn this process through. I can send a broadcast on the local subnet with a discover message to see if there's a controller there. I can use locally stored controller IP addresses. We call that priming the IP. That would assume, though, that you've already had a successful join to the controller previously, and then you've been reprimed with new controller information. We can use DHCP option 43. That's the vendor option with the TLV values, the type length value field. Or I can use DNS resolution, the Cisco-CapWAP-controller option. Once the AP's gathered a list of all the controllers, it's going to, of course, select which controller to join. And you can have up to 3 different controllers: a primary controller, secondary, tertiary, and so on. So we'll take a look at that. We only have 1 controller in our instance, of course. APs get their IP address either statically or through some sort of DHCP process. That occurs before we even go out and try and do any kind of CapWAP discovery. In broadcast mode, the controller-based AP sends a CapWAP controller discovery request to the local LAN. All of the wireless LAN controllers in that local subnet will receive that packet, and they're going to all send out a discovery response. Other option, locally stored either V4 or V6 information. We call this priming, like I said, of the primary, secondary, and tertiary controllers. That would be stored in the non-volatile memory of the AP. This would assume, like I said, I say that a lot, that you've already successfully joined a controller and you were able to actually access the AP GUI and set up that configuration. Once the controller actually associates, once the access point actually associates with a controller, other controllers can be grouped to form things like mobility groups. And then once we associate to the controller, the AP can learn IP addresses of other members in that mobility group, and we can go through the whole process of adding that redundancy. I would say the most common option is, and I'm not saying it's the best option, but the most common option is to use the DNS mode. If you don't want to have DNS reliance, the DHCP vendor option mode is very good as well. We actually, or Mike, you actually configured, and Tiju, you'll do this later, you guys actually configured the vendor option mode as part of the DHCP pool in the switch configuration, right? And Mike, I was curious, did you calculate the option 43 address, or was it in the lab guide? Because I noticed that it was configured. I was just curious of whether or not you did that.
It was in the lab guide.
Okay. But you do recall the process for calculating that, right? It's most likely almost always going to start with F104.
Oh, right. Yeah, I gave a chart.
Yeah, and then you have the last 32 bits of the MAC address become the last the 32 bits of the IP address. You just have to convert it. So with this DHCP vendor option, when the AP sends out a DHCP discover request, it uses that vendor option in the DHCP transactions that occur between the DHCP server and the client. If the DHCP server is configured to respond to those options, in other words, it's set up as part of that scope, it's going to send the IP address of the controller in the DHCP acknowledgement message. It's actually sent in the DHCP offer message. So the first step in DHCP is to discover, the second step is the offer, the third step is the request, and then the fourth step is the acknowledgement. So actually, it's sent in that DHCP offer message. The AP uses that information to send a unicast discover message to each of the controllers. The vendor string that's used by the APs to request that vendor option depends on the model, but you can have several options in there. We only had one in our example, but if you did want to add multiple controllers, you would simply put a comma, add a second one under the option command that you saw within the DHCP scope, put a comma, add a third command, and so on. The other choice you have, DNS, right? Set up option 6, set up option 15. If you recall, option 6 was the DNS option. Option 15 was the domain name option. The AP obtains its IP address of the DNS server from DHCP, and then it uses the Cisco-capwap-controller.local domain to discover the IP address of the controller. All right, make sure that the controller is set to the current time. If the controller is not set to the current time, the access point might not join the controller because, if you're using certificates and whatnot, the certificate might not be valid. When we did the setup, Mike, incidentally, and also for you, Tiju, when you go do this later, the AD server is in the lab, the 11.11, is your provides network time as well. So when you go through the initial configuration of the controller in the CLI, use that address as the address. I'm going to compile a list of all the things that I discovered in those issues that we saw with the first lab, and I'll send you guys some updated information about that. When the AP moves into this discovery phase, it sends a discovery to each of the controllers in the list, however that list was compiled. All right. There is a predefined method, though, that the AP uses to select the controller when it registers. Obviously, it's going to try to associate first to the primary controller, assuming that that's already been primed. If it doesn't register with the primary controller, it'll go to the secondary, and then it'll go to the tertiary controller. If the AP is not primed with controller information, it's going to look for a master controller. Let me show you that real quick. Let's see, right, pull it up here. When you go into the controller configuration, one of the settings that you can establish under the controller configuration is that you can identify the controller as a master controller. Let's see, should be a checkbox. I have an older version of software, so sometimes I can't remember where things are here. Let's see, master controller. I think it's under advanced, if I'm not mistaken. Yeah, master controller mode. So you would just check this box and identify this controller as a master controller. It's just part of in the communication that occurs between the AP and the controller. This is just an option that is identified in that process. And essentially when you do select a controller in master mode, that is the only controller that the APs will try to join, even if they see other controllers in the group. We usually will do this, check this box, if we're doing an initial setup and we're just trying to get all the APs primed and all the APs configured. I don't want to have to see if they're connecting to one controller or a different controller. And then once I've got mobility groups set up and everything else is configured, then I'll go and disable this option so that we can do controller balancing, load balancing, and whatnot. But make sure you don't check that. It's okay if you check it if you only have one controller. It doesn't really do anything at that point, but that's what that is for, master controller mode. And notice here it says this controller is currently not. Obviously it's not checked. Check it, apply. No big deal. It wouldn't affect really anything, particularly in my environment where I only have a couple of APs and one controller. So it looks for the master controller. Finally, if there's no prime controller and there is no master controller, the AP is going to essentially select the least loaded management interface for all the controllers in that process. What defines the least loaded wireless LAN controller? Well, in the CapWAP discovery response that you get from the controller sends a bunch of information about its AP load. Essentially, it's the number of APs that are joined at that particular time to the controller. But it's not totally based on the number of APs, because you know that 2504 only supports 25 access points. So it's a percentage of load. So it's based on the capacity, the number of wireless clients, and how many APs are joined at that particular time. So the AP will attempt to join the least loaded controller at that time. Essentially, if you're not priming the AP and there's no controller information configured in the AP and you have no master controller, this is essentially what you're going to default to. We're going to join the least loaded controller. All right. If the APs are not primed, which is the case when they're out of the box, right? If the APs are not primed, and they're using the broadcast function to find the controller, then the AP will ultimately load balance between whatever management interfaces exist for each of the controllers. The first AP in this example registers to controller number 1, the second AP registers to controller 2, and so on. Let me just state one thing for the record here, though. It is broadcast based, what we're talking about here. So controller discovery cannot occur across VLANs with this particular mode of discovery. And the IP helper address that you can use to relay things like DHCP does not work with CapWAP. So IP helper address is not going to allow you to extend those discovery messages beyond your subnet. This whole process that you see depicted on the screen here assumes that there's only one interface capable of management per wireless LAN controller, and also that there are more than 3 APs already registered. Right? Load balancing actually does not activate until there's a minimum number of at least 3 APs associated to a particular controller. All right, so even though they kind of described AP1, AP2, AP3, AP4, we're assuming that there's already a bunch of APs joined to these two controllers, and that's how the load balancing algorithm would work. The controller answers with the AP capacity, occupation during the discovery process. The AP uses that information to determine the remaining space on the controller, and then it tries to associate to the least loaded controller. When AP1 boots, it discovers both controllers. Each of them have the same load in this case, 0 APs, so it joins the first, it joins whichever controller answers first, essentially in that discover process. When AP2 boots, it discovers both controllers as well, and then it goes to the least loaded controller, 0 APs instead of 1, versus controller 1 and controller 2, so it goes ahead and joins controller 2. When AP3 boots, discovers both controllers, you get the idea. All right. The load is a relative value. Like I said, a 50 AP controller having 10 APs has about a 20% load, whereas a 6 AP controller having 3 APs has a 50% load, and that would be considered more loaded, obviously, even though it has fewer APs associated to it. All right. Okay. If the master controller is configured, I already described what that means. The process changes completely. All APs that are not primed, in other words, don't have a controller identified, access the controller via layer 2 or layer 3 via broadcast, and they'll automatically join whatever controller is marked as the master. This allows you as an administrator then to go in and prime those APs after the fact. But you don't have to go to a bunch of different controllers to do that, right? You can just, everything is going to connect to one controller. All right. Now, there are other ways to provision access points without having them connect to a controller initially. All of the Cisco UAPs, what we call UAPs, the Universal Access Points, they allow for basic, well, I would say simple configuration, right? Now, there are two priming methods that we can use for these access points. You'll notice that when an AP is, well, that's what they're trying to depict here, right? When an AP is manufactured, it's not tied to a specific region. And it goes through the supply chain unassigned. That's what UX means. Dash UX means universal domain. Once it goes, once the AP is going to be sold to a customer, it gets a regulatory domain fixed to it, like dash A, dash E, and so on. And that's shipped with a permanent pre-configuration for regulatory compliance. In other words, you can't, as an end user, change the regulatory domain. So make sure that when you're purchasing access points, either for yourself, online, especially on eBay, that you're getting one that's identified for your regulatory domain. Once you receive the access point, there's a couple of things you can do. You can do manual priming, and we can do that using what we call the Cisco Air Provision mobile application, or you can do automatic priming through something through that NDP propagation, the discovery propagation. All right. Both APs and both the APs and the wireless LAN controller need to support universal mode. That's done. It's essentially assumed, being that these access points were designed to connect to the wireless LAN controller anyway. Now, you can manually prime these universal access points using the Air Provisioning mobile application. It's a smartphone application. You have a smartphone running the Air Provision application and a universal AP that needs to be on the same wireless LAN as the smartphone. So you need to have them connected together. Essentially, you plug in the AP. It's going to be advertising an SSID. The smartphone will connect to that SSID. And it uses the geographical location of the smartphone to decide the regulatory domain for priming that AP. Okay? Once it's primed, though, done. You can't change it. All right? Air Provision uses the GPS coordinates, the mobile country code advertised by the cell phone network towers, et cetera, to prime that AP. Any universal AP that was previously primed to a different country, you can manually, you can't change it. You can't change it through the wireless LAN controller, but you can manually reprime that to a different country configuration. You do have to use the app though, so it's not something that you can change in the WLC. So typically what will happen for new installations, especially if you have universal APs, you manually prime at least one AP in the radio frequency neighborhood. After that AP has been manually primed, then all the other APs in the same radio frequency spectrum get primed via automatic priming. If automatic priming fails for some reason, I don't have enough, we're not getting a strong enough signal or whatever reason, then you can manually prime those APs as well. I have a couple of 3702s sitting upstairs that when I plug them in, they don't connect to the controller because I haven't primed them. So that's something that I have to do, but that's part of the process. Okay. All right. So I don't know if you guys have had a chance to kind of go through any of these processes. Obviously, being that these are virtual labs, this is not something that we're physically going to be able to do. It is pretty straightforward. It is a pretty straightforward process. The next slide will kind of take a look at what that looks like. Works on Apple, Android, Windows Phone, if anybody actually still has those. It will not run. Have run into this problem as well. This product, Air Provision, will not run on a jailbroken phone. And that's just a security mechanism that Cisco built into the application. So you actually may run into a situation like that where you try to jailbreak a device and now you can't run this application anymore. Of course, you have to have access to the internet. Usually with cellular data, that's fine, or Wi-Fi. You have to have GPS enabled. If GPS is not enabled, that's the preferred method of being able to identify your physical location, but it can use the mobile country code advertised by the cell phone network and the towers if need be. To determine the location, that's really what the objective is, right? I use the GPS or this smartphone function to identify the location. During the manual priming process, the smartphone obviously has to be in range, has to be associated to a cell phone tower, so you have to have signal. No priming in the middle of nowhere, basically. All right. I joke, but you could run into situations where that might occur. You can go out to some branch office in the middle of nowhere and you don't have any cell phone coverage. Internet would be fine though. All right. Automatic priming relies on this protocol called the neighbor discovery mechanism. That was the second option. Assuming that another AP in the RF area has already been primed, you can use this neighbor discovery mechanism to prime the other APs. A primed universal AP sends out regulatory domain information, country configuration, and it does that in an 802.11 frame in the actual beacon frame. So any lightweight universal AP that's waiting to be primed can identify those universal APs in the neighborhood. They learn their domain configuration from those already primed APs, and then they configure themselves. For brand new installations, the very first universal AP to be primed has to be primed manually using the steps that we talked about on the previous couple of slides. Once that first universal AP is primed, any other unprimed AP boots up in the same neighborhood, receives the same priming information through Cisco NDP, the Neighbor Discovery Protocol, and it gets primed. If automatic priming doesn't work, then you're going to have to prime the AP manually again. Again, you're not configuring the AP with a bunch of configurations. You're just basically identifying its physical location. All right? All of the Cisco wireless controllers are designed to provide you high availability for the APs. So in the event that a controller fails, the AP associated with that wireless controller will migrate to other controllers if those controllers have enough licensing and capacity to support that particular AP. The APs will then fall back to the primary controller if it does come back online. You can disable the fallback feature. We don't usually do that, but you can disable the fallback feature. APs basically do this. They monitor the status of controllers by sending hello packets. Periodic, these are called heartbeats. They're sent out every 30 seconds just to make sure that the controller is available. If the heartbeat is acknowledged from the controller, great. If one acknowledgement is missed from the controller, we resend the heartbeat 5 times in 1 second intervals. So it's kind of like a panic mode, right? Oh no, I lost a heartbeat. Okay, I'm just going to start, blowing up your phone, I guess you can call it. So we do that for five times every 1 second. If an acknowledgement gets received after the 5th retry, then the AP declares that the controller is unreachable. It's going to go ahead and search for a new controller. All right. Both that retransmit interval and the retransmit count, those are configurable values. And you can fine tune that behavior, although there's really no need to change that. I suppose about the only thing that you may want to change is that initial interval, right? The 30-second interval. You may want to change that to a lower value. You can choose values between 3 and 8 for the retransmit count. 3 is the default. The value is between 2 and 5 seconds for the retransmit interval. And again, 3 is the default. For the heartbeat, 1 to 30 second timeout period. So 30 is the max that you can establish. What's the benefit of using a smaller value? Well, if you use a smaller value, that's going to allow the AP to discover unreachable controllers faster, but you're going to get a spike or an increase in administrative traffic, and you're going to use additional bandwidth for that. In addition to the heartbeat process, the AP maintains a list of backup controllers. I can show you. We go to wireless, and we go into our wireless access point. And you should be able to see, I believe it's under advanced actually. Where the heck is it? Oh, high availability right here. So this is where you can put in the primary controller, secondary, tertiary controller. This is said to be primed, right? Because the information is part of the AP configuration, and it won't go away even if I reboot the access point. All right. So in addition to the heartbeat process, we have that ability to list backup controllers, and we can send a discovery request to each of those in the list. The time period for these discovery requests are sent, that's a configurable value between 30 and 3600 seconds. Just to make sure that the secondary and tertiary controllers are online, the default value is 120 seconds. Okay. Now you can set that through the GUI, you can set that through the CLI, and it specifies the amount of time that a controller has to respond to any kind of discovery request of the AP before the AP assumes the controller can no longer be joined, and it waits for a discovery response from the next controller in the list. When an access point declares the primary controller is unreachable because of those missed heartbeats, it'll select an available controller from the backup list. So you can statically configure that. I just showed you the screen, the primary, secondary, and tertiary. Or you can do statically assigned configurations by the controller. So you can say which controller is my primary backup controller, which controller is my secondary backup controller. If the primary, tertiary, primary backup, secondary backup controllers are unavailable, the AP is going to go back to the dynamic CAPWAP algorithms to connect to it, the kind of the least loaded available controller. All right. So I just showed you kind of this screen here with regard to high availability, primary controller, secondary, and tertiary. You'll notice there that there's also a drop down for AP failover priority. We see that right here. Low, medium, high, and critical. All right. Each controller has a defined number of communication ports for the APs. So when you have multiple controllers with unused AP ports that are deployed in the same network and one controller fails, that dropped AP automatically pulls for an unused controller port and associates with that unused controller port. So you can actually configure the wireless network so that the backup controller recognizes a join request from a higher priority AP. Remember, this is configured on the AP level, right? See details for centralized AP. So this is something that would apply to an AP. And if it's necessary, it will actually disassociate a lower priority AP to provide availability for the higher priority AP. So let's just kind of break down the 4 options here, right? Low assigns an AP to the level of 1, lowest priority, medium a level of 2, high a level of 3, and critical a level of 4. All APs are set to a priority of 1 by default, so you have to go in and assign those values. So let's say, for example, I've got my enterprise wireless network, and I've got a 2504 controller that supports 25 APs, and I've got 25 APs provisioned on that controller. And then I have another 2504 in failover mode, or a secondary controller that I can use as a backup, and that is a 2504. It also supports 25 APs. And I might have 20 to 25 APs provisioned. Well, let's just say 20 APs provisioned on that controller. I then have to decide out of the original 25 which 5 APs are most critical for business operations. And I'll mark them with the AP failover priority of critical, so that in a failover event, if I only have 5 available slots on the secondary controller, I can guarantee that those APs are going to get registered, and we get service provided. All right. When the wireless controller AP fallback option is enabled, and you can see that's under the general settings for the controller. Those are some of the settings. Obviously, Pod 1, WLC, we called ours something else, but AP fallback is enabled. APs are going to return to their primary controllers after there's a failover event. It's enabled by default, and typically we don't change that value. It's not really something that kind of really affects production. The fallback option doesn't really break wireless necessarily. Just keep in mind, when an AP falls back, there is a brief window of time, even though you may not notice it, of about 12 to 30 seconds, depending on the timer configurations. So the clients could see an interruption of service for that time period. If for some reason connectivity to the primary controller is unstable, you might even see a situation where I join that controller, then I fail over, then I fall back, fail over, fall back. So that would be one of the other reasons that you may choose to disable this particular feature. Okay. One method of providing redundancy is to assign primary, secondary, and tertiary controllers. You need to specify the name and the IP of the address of the controller. Make sure the controllers are not in the same mobility group. Otherwise, it's not really providing failover. It's just part of a single group. The pros, yeah, you get more uptime, I suppose. But the downside is it's stateless switchover, meaning that when a failover event occurs, all the clients have to reassociate, reconnect, etc. And it requires obviously more money. You got to buy more controllers. They're configured independently. There's various reasons that you may consider doing one or the other. Okay. I don't typically see more than one secondary controller. Very rarely do we see an implementation where they actually have a tertiary controller as well. All right. Now, if you are going to do N+1 failover, which is what's kind of depicted here, right? You've got 3 controllers and they're all kind of failing over to each other, right? The primary is for the access points on the left is controller A, failover to B, failover to C, center, controller B, etc. You get the idea. It's kind of everybody's kind of scratching everybody's back, making sure that we have the failover. There are some best practices that Cisco recommends. The most common design is N+1. That means you have a redundant wireless LAN controller in a separate location, so a NOC or a data center. High availability parameters to detect a failure. Make sure it's fast, minimum of 30 seconds. That's a setting that you set in the global wireless LAN controller settings. Use AP priority in the event that you don't have enough licenses, which is oversubscription, because while each controller is operating independently, you may have enough licenses, but on a single controller, you may not have enough licenses to support all of your APs. All right? Make sure you also use the controllers that actually support high availability, which is the 2500s, the 5508, the 7500, and the 8500. All right? There are some high availability SKUs that you can use, so you don't have to pay for a bunch of extra licenses simply for failover. You just use the high availability SKUs to provide that failover. All right. Most customers, and this is typically what we see in most of our clients' networks, high availability is provided with one-to-one redundancy. Basically, you have a active and you have a standby. Stateful switchover of access points is supported in this particular scenario. One controller is configured as the primary, the other is configured as the secondary. So after you go through and you enable high availability, the primary and secondary controllers get rebooted, and during that boot process, the role of the primary controller gets negotiated as active, and the role of the secondary controller gets negotiated as standby hot, what we call standby hot, or just standby if you don't want to use the hot part. If this failover event occurs, if you see a switchover, the secondary controller becomes the active controller, primary controller becomes the standby. After that and further subsequent switchovers, the roles are interchanged between the primary and secondary controllers. So there is preemption enabled in this particular case. The reason for switchovers could be you do it manually or some sort of network failure, obviously. Very important concept when you're running this high availability. During AP, stateful switchover, all the AP sessions are statefully switched over and the clients are deauthenticated and reassociated with the new controller. But that's done automatically without the client having to intervene. So what happens is the standby hot controller is basically monitoring the health of the active controller through heartbeats, through keep alives. And that's done through the wired connection, of course. Or you can have dedicated redundancy ports that you can use as well. Both controllers share the same configuration, IP address, management interface address, and so on. Sounds like a better option to me. There is no preemption functionality. Preemption means that I fail, you take over. If I come back online, I take over again, even if you're still functioning. That's what preemption is. With the case of the wireless controller, there's no preemption functionality. When the wireless controller comes back, the one that was previously the primary controller, it does not assume the role of the active controller anymore. It will negotiate its state with the current active controller, but then it will transition to a standby state. The active and the standby decisions is not automated. What I mean to say is that the active standby controller is decided based on the SKUs and the UDI, the unique device identifier. So a wireless LAN controller with a high availability SKU will always be the standby controller for the first time when it boots and it pairs up with a controller that's running a permanent count license. Does that make sense? I didn't really get into the description of what a high availability SKU is, but it is a product that you can purchase from Cisco that essentially eliminates the need for you to buy a permanent license for users, for clients, or APs in this case. So you have permanent licenses installed on one controller, and then you have the high availability SKUs that are installed on the other controller. All right. Now you can override that you can also establish active and standby decisions based on manual configuration as well. Some of the other things we see on the slide here, you can see a lot of the different enhancements and so on. I'm not going to read all of the bullet points there. You can pause the video and kind of take a look a little bit if you'd like. It's just a lot of information there to consider. Okay. The redundancy port is used for configuration, operational data synchronization, role negotiation between primary and secondary controllers, and so on. Not all controllers have redundancy port built into them. Certainly the 2504 does not, but some of the higher end controllers have these redundancy ports built in. The purpose of the redundancy port is to check for reachability. We send those keep alive messages every 100 milliseconds, well, that's a default anyway, from the standby hot controller to the active controller. We're not talking about AP failover at this point. We're actually talking about stateful switchover between a primary and an active controller. So these timers are a lot different, and it makes sense that they're much, much faster because of the state information that needs to be maintained. All right. The failure detection time gets calculated if, I don't know, I guess I could describe this. If the keep alive timer is set to 100 milliseconds, we take that value, we multiply it times 3, that gets us to 300. We add 60 seconds, that gets us, or milliseconds, that gets us to 360 milliseconds, plus we add or compensate for jitter, another 12 milliseconds. So the failover actually ends up being about 400 milliseconds. All right. Make sure you have enough bandwidth between the redundancy ports. It needs to be at least 60 megabits or higher. Okay. All right. Hold on one second, gentlemen. And finish up. When you're dealing with the failover stuff, I've personally, as an engineer, have never really modified any of these particular values. Cisco does recommend that you only change them if you see that it's insufficient for what you're trying to accomplish. Okay, or you notice that these failovers are taking too long or whatever it might be. But like I said, make sure that you have at least 60 megabits a second or higher on those RP ports, those redundancy ports, because of the amount of data that's being sent back and forth and established between them. Also make sure that it has an MTU of 1500 or higher as well. Okay. The failure detection time can be adjusted, not really necessary. If you're using a WISM, the wireless service module, you have some failover options as well, but obviously in this particular case, it's not based on physical cable connection, it's based on the backplane of the 4500. So you would put a WISM in slot 8, and then you would put your hot standby WISM in slot number 9, okay? Very similar configuration in that sense. If you're using the converged access, you can also deploy failover over a VSL link. That's VSS over a layer 2 link. High availability, meaning AP stateful switchover, can be deployed with secondary and tertiary controllers as well. Both active and standby controllers get combined into the high availability setup, and then they should be configured essentially as the primary controller. Only on the failure of both the active and standby controller in this high availability setup will the APs actually fall back to the secondary and the tertiary controller. So you can still have additional redundancy. You're just not going to get that stateful switchover option that you see in with the high availability piece. All right. Another thing that a lot of people get confused about, and it's something very important to understand, is what does it mean to change the AP mode, right? And you can see from the drop down here, there are many, many different modes of operation. You got local mode, you have flex connect mode, monitor mode, rogue detector mode, sniffer, bridge, etc., right? So many different modes of operation. Some modes will perform specific functions. Some modes allow you to service clients. Some modes do not allow you to service clients. So one of the things that we have to do is kind of go through the process of talking about what each of these modes represent. Now, we may not get into it in a whole lot of detail right now because there are some lessons that talk about some of these specific modes in more detail. After the AP's joined, right, it's discovered the controller, it's joined whatever controller it's decided that it wanted to join, it is going to default typically to the local mode. That's usually the normal mode of operation that an AP will operate in. APs controlled by the controller do support several different modes of operation though, right? Each mode has its own purpose. Like I said, different models might even not support some of these modes, and some APs might support some of these modes. Changing the AP mode, as you can see the tab there, you go under wireless, go under your access points, go under all APs, select the AP, and then you can change the mode of the AP under the general tab. Local is the default operation for most Cisco APs when they connect to the controller. If we're operating in local mode, the AP allows both client data services and it monitors all of the radio frequency spectrum as well. This is why it's typically the preferred mode, because I want to be able to provide RF spectrum data, and then I also want to be able to service clients. Off-channel scanning is defined as the channels that are not actively being used by the AP, is essential to this whole concept of radio resource management, right? Talked about transmit power control, dynamic channel assignment, looking for interference, .11 interferers, as well as non-802.11 interferers, and so on. So the AP will go through it and it'll scan while it's servicing data on the active channel for clients. It'll go onto those off channels and scan for information. All right, but there is some timing involved in this process. All right. And that timing is not something that you can configure. It's just part of the overall process. And we'll go through it on the slide here, but it allows us to identify essentially the process and how do I allocate time slots to be able to gather information about the spectrum, right? While I'm still servicing clients as well. So in local monitor mode, APs are set up to host client data. They're also set up to monitor traffic at the same time. We accomplish this by using a time scale of 180 seconds. 180 second cycle, I guess you could say. All right, and for the BNG radio, that means that the AP is going to stay on its assigned channel for 13 seconds based on the number of channels that exist. Okay. We scan that channel, then the next channel for 60 milliseconds, then we return to the assigned channel for 13 seconds, and then I essentially repeat that process until all the channels have been scanned. 802.11a does the same thing, but we only allocate 10 seconds because of the high number of channels that we have to scan. So essentially we're just kind of bouncing back and forth between these different frequencies, send some data, clients, scan, send some data to the clients, scan, send some data to the clients, and scan. So you can see in the top diagram, channel 1 is the channel that's servicing the clients, obviously, and channel 2, 3, 4, 5, these are the off, the channels that are not being used by the clients. All right. On the bottom one there, you see that channel 36 is used in our case, so we're going to scan the non-used channels 40, 44, 48, 52, and so on. This is all done under 180 second time period though. The controller allows for the configuration of that round trip time, and you can even identify which channels you actually want to scan if you don't want to go through all of those off-channel numbers. Okay. ELM stands for Enhanced Local Mode. That's another function. It's not part of the AP mode dropdown. It's what we call an AP submode. And you can see there's a couple of, well, there's really only one option, WIPS or none. So when you configure ELM, you're actually adding IPS detection on channel, which means that attackers can be detected on the channel that's actually servicing the clients. For all other channels, ELM provides kind of best effort IPS detection. So it's every time that the frame, every frame, excuse me, that goes from the radio that goes off channel for a short period of time, it's going to look for some signatures for different types of attacks. While off channel, if an attack occurs while that channel is scanned, then the attack would be detected. But that's only a very, very short time window, if you recall from the previous slide. So you could have a 2.4 gigahertz radio that's operating on channel 6, for example. The AP is going to constantly monitor channel 6, and any attacks on channel 6 will be detected and reported. But if an attacker attacks channel 11, while the AP is scanning channel 11, that attack will be detected. If I attack channel 11, if channel 11 is not being scanned, then of course the attack might be allowed to go through. Just a point of reference here, and they have it in the big box right there. Simply selecting the submode does not actually enable WIPS. You have to have a Cisco MSC or Prime infrastructure with WIPS licensing to get this functionality. So just simply turning on that feature, even though it doesn't give you a warning when you do, simply turning on that feature is not going to enable that feature necessarily. Well, not necessarily, it definitely won't. Okay. FlexConnect, another mode of operation. I've already alluded to what this is a couple of times. It's an AP solution for branch offices or remote offices. Essentially, a FlexConnect AP allows you to configure and control the APs in a branch or remote location, whatever it might be, that are provisioned over a WAN link without having to actually deploy a controller at that remote location. So client traffic on a FlexConnect AP can be switched locally at the AP, or it can be tunneled back to the controller. If you have sufficient bandwidth over the WAN, you may choose to send all the traffic back to the controller so you can control what happens to that traffic on that local LAN. But if you don't have a lot of bandwidth over the WAN, maybe you just want to switch that traffic locally at the local switch, and you can set up some security properties there. That's what a FlexConnect AP does. That traffic could be tagged or it could be untagged, it doesn't really matter. But when you're connected to the controller, when a FlexConnect AP is connected to the controller, it acts just like any other lightweight IP. The only difference is, am I tunneling the traffic back to the controller, or am I switching the traffic locally? Okay? If the controller is available and you've configured the process, all the traffic gets tunneled back to the controller. But if connectivity to the controller is lost, the FlexConnect AP can then automatically start switching client data traffic and perform client authentications, because that's another very important concept, locally on the AP. We call that standalone mode. So it's not a mode that you configure, but it is a mode, an operational mode that the AP can be in. I guess you guys understand that capability, right? You can still have centralized administration of the AP. You can keep local traffic local, so it doesn't consume WAN bandwidth, or you can use it in the event of a failover. All right. Now, interestingly enough, AROS 8.0 allows the use of FlexConnect from the local mode operation without the AP rebooting. Used to be where if you wanted to switch to FlexConnect mode, you would have to actually reboot the AP every single time, and vice versa when you wanted to go back. Okay. Another option with the deployment of the AP is to deploy the AP in what we call Office Extended mode or Office Extend mode, OEAP. Very simple, cost-effective solution to extend the wireless network to your remote locations over a VPN. All right. And we'll talk about the details of that. I don't know that we'll get into a ton of detail, but I want to at least give you an idea of what it looks like. So Office Extend, if you look at the diagram here, it's a little bit different than what we talked about with the FlexConnect option. Because in Office Extend, your headquarters is connected via, well, we don't have a private WAN in this case, right? The access points being deployed in a home office or some, remote location that all they have is just an internet access. So what this provides, Office Extend access points provide, is the ability to plug in a router that gives you some sort of internet connection. And then what happens is the AP establishes a secure tunnel back to the corporate network so that I can access my data, my voice, my video applications as if I'm sitting in the office. But I don't have to have a special VPN connection. I don't have to have a firewall necessarily in place that I would have configured myself, right? It's basically a FlexConnect configuration, right? Because you're still allowing the wireless traffic to get switched locally within the LAN, but it provides that additional security, all right? So you can access the internet wirelessly. You don't have to add any additional devices. In addition, you can even create your own SSIDs, which get routed locally to the internet, and then you can have your corporate IDs still identified. All of the supported AP models, only with integrated antennas, can be configured with this OEAP operation. There are 3 basic features that exist with OEAP. You've got your basic firewall features. That's going to allow you to do port and application protection and so on. Split tunneling capabilities, so that if you want to reach the internet directly, that doesn't have to go through the VPN over to the corporate network, and then all your VPN traffic would be routed over to the corporate network, and then quality of service for voice. The 600 series OAEP access point was actually specifically designed for this mode of operation, and currently offers things like single sign-on support and so on. Another mode of operation that you can have with your access points is something called monitor mode. Monitor mode is typically an operation that's designed to allow APs to exclude themselves from actually servicing clients, right, and infrastructure pieces. But it allows us to monitor the radio frequency spectrum. In fact, in monitor mode, that's exactly what the access point's designed to do. It's acting as a dedicated sensor for all the context-aware services. That context-aware would be like location-based services, rogue AP detection, IDS, and so on. Like I said, when you're in monitor mode, the AP does not serve clients. It continuously cycles through all of the configured channels, and it listens on each channel for about one second or so. It's a little bit more than 1 second. Monitor mode APs can also be configured with 2 sub-modes of operation as well. One sub-mode is called tracking optimization monitor mode. That's going to optimize the monitoring for triangulation of RFIDs and location identification. And the other is just monitor mode. In tracking, IPS monitor mode, excuse me, I'll talk about that one in a second. In tracking optimization mode, the channel list is specified, and then we monitor and scan all of those individual channels. In WIPS monitor mode, we configure that from the GUI or through Prime Infrastructure, we scan all the channels in the DCA list. The DCA list is my dynamic channel assignment list. The per channel scan time here is much, much shorter because we're looking for attacks. We're looking for things that are occurring. It's about a quarter of a second or so in that particular case. Okay? Keep in mind, if you do monitor mode, regardless of the mode that you're monitoring in, you cannot service clients in that case. Some customers do like to deploy APs throughout their enterprise just for that function, just to go into this monitor mode function. Rogue detector mode, the AP radio is actually turned off. This is an interesting concept because you're thinking, well, if I want to detect wireless, rogue wireless access points, I might want to listen to it over the wireless network. But that's actually not what happens. The radio is actually turned off and the AP listens to wired traffic only. Because the radio is turned off, you can stick this rogue monitor AP anywhere. It doesn't have to be out ceiling mounted. It doesn't have to have antennas positioned strategically and so on. The rogue detector, the way that it works is it essentially listens for ARP packets on the wire, and it caches all of those ARP packets. That address cache is used to determine if the layer 2 address of a rogue client or an AP is present on the wire. Now, keep in mind, ARP is broadcast based, so you would have to have a rogue detector AP installed in each broadcast domain if you did want this feature available for multiple subnets. We can put the AP in to avoid having to place rogue APs, rogue detectors, excuse me, in multiple VLANs. We can use a trunk port, so we can actually trunk that traffic, so I can hear all the ARP traffic from multiple subnets. But my point being, my previous statement was that you definitely need to have either that configured, so trunk interface, or you need to have a separate rogue detector for each one, for each subnet. Okay? If layer 2 addresses are matched, if we find a match, the controller generates an alarm that's going to identify that rogue AP or rogue client as a potential threat, and then we can take further action based on that. Okay? APs in this mode can also be used in an area where the company doesn't want wireless access. So maybe you don't necessarily want to scan your network, but you want to see if, you don't want to, you're placing the rogue detector into an area where there are no wireless clients and there are no wireless APs, but the whole concept of rogue is what? The concept of rogue is that, well, somebody's putting something somewhere that they're not supposed to, right? That's kind of the whole point. All right, so it doesn't necessarily have to be in an active wireless environment. I guess that's what I'm trying to say for this particular mode. All right. Sniffer mode is also another mode of operation. With sniffer mode, the AP joins the controller and then it's placed into a promiscuous mode of operation. So it can capture essentially all the 802.11 transmissions that are sent over the air and that it receives. Those packets, including things about timing, signal strength, they're going to get forwarded to a remote PC, and then on that remote PC you're probably running an application like Wireshark or whatnot, so that you can analyze those packets, you can decode the data packets, get additional information about what's happening on the network, and so on. OmniPeak, that's an application that you can use. Air Magnet Enterprise Analyzer is also an application you can use. Both of those are licensed applications. You could choose to use Wireshark. Wireshark is a free application that you can use. So each AP in sniffer mode monitors a single 2.4 gigahertz channel and a single 5 gigahertz channel simultaneously. When you're in this mode, the AP isn't capable of supporting clients, and it consumes one AP connection on the controller that AP joined. So even though we're not servicing clients and we're not really doing anything else except for just doing packet captures, keep in mind it will take up one of those slots on your controller. You can enter a sniffer mode by selecting it from the AP mode drop-down menu. Wait for the AP to rejoin the controller. And then, once that AP is reconnected, you can select the channel on which you want to do the scanning, and then you enter the IP address of the remote station where you want to send the packet captures, the analysis. The controller checks the IP address and the MAC address in each packet, compares those to the addresses that are registered with the controller, and then it forwards the packet if both of those match. So you have to disable IP to MAC address binding in order to use this sniffer mode operation as well, which is not something that's normally turned on anyway. All right, so we talked about monitor mode, we talked about flex connect mode, we talked about open mode, now we talked about monitor mode. Let's talk about, bridge mode now. Selecting bridge mode, if you go into the operation of the AP and you select bridge mode, the AP is going to operate as an MAP, right? Like a mesh access point. Wireless mesh networks carry traffic for clients. They carry, of course, their Ethernet port traffic, and they carry the traffic for the APs that are connected to the physical infrastructure. If you remember, we called those RAPs, right? The APs that have a physical connection to the infrastructure and then have a wireless connection to the rest of the world. The client traffic terminates on the controller, as always. The Ethernet traffic terminates on the Ethernet port of the mesh access point. MAPs support multiple deployment models. You can set them up as a wireless mesh. You can do wireless LAN backhauling if you choose, point to multi-point wireless bridging, and also point-to-point wireless bridging. Just make sure, obviously, I mean, there's other integrations that have to take place. You have to have other access points that are participating in this network for it to function correctly. If you're operating as an indoor map, that's supported on only a few Cisco access points, but it's supported on all of the wireless LAN controllers. Operating 802.11ac, that's going to use 80 megahertz wide channels for the backhaul traffic that's being sent across the mesh network. So you have to make sure that you've allocated the appropriate resources for that. In order for you to establish a mesh network, whether you're doing it inside or outside, and I just mentioned this because it's a little bit of a misconception that you can set up an MAP without having any other components in the network. You have to first have an AP connected to the network and it's allowed to join the controller. Once the AP joins the controller, then you can change it into bridge mode. New firmware is going to actually have to be applied to the AP. The AP is going to reboot. It'll join the network as an MAP, a mesh access point. In order for that mesh network to form, this is the very important part, you have to have at least one AP placed into operation as the root access point. That's the RAP that I had mentioned before. Remember, a root access point has a wired connection to a distribution system that allows us connectivity to the wireless LAN controller. Once the AP is in operation as a root access point, the mesh network can form, and then the mesh AP will use what we call the AWPP protocol to determine the radio path. That's kind of like that, I don't want to really call it a routing protocol, but it's very similar to the concept of a routing protocol that allows us to then communicate over the best possible path back to the wireless LAN controller and the infrastructure. All right, make sense? I don't know if you guys are too involved with setting up mesh. I doubt it. It's not something you typically configure. You might run into a scenario where you need something like that, you know, maybe a parking garage or something like that. All right. All right. Now there is another mode of operation. It's called Flex plus Bridge mode. And you can kind of guess what that mode of operation looks like. Flex plus Bridge mode it allows Flex Connect behavior across a mesh-enabled AP. So it extends the wireless network, but it also uses all of those standard Flex Connect features that we talked about when we talked about an AP operating in Flex Connect mode. You can have CapWAP connected. The wireless LAN controller is reachable through CapWAP. That's your control plane functionality. Or you can do standalone where CapWAP is not connected and you can't reach the wireless controller. That's where the Flex Connect piece comes into play. On the data plane side, you can do split MAC functionality. Data traffic goes to the wireless LAN controller, and then you have local traffic, the real-time stuff managed by the AP, or you can operate the data plane support in local mode where all the data traffic is done through local switching from the root AP, not the MAP, but the root AP. Diagram looks a little confusing, but you can kind of see what's happening here in this particular case. You got a tablet and a PC connected to a mesh AP. The PC's traffic is being sent through the controller over to your centralized network, but the tablet traffic is being handed off onto the LAN without having to go to the controller for the direct Wi-Fi printing and so on. All right, so you can have a mix of flex and bridge mode configurations, I have a couple of different options. Another mode of operation called SE Connect mode. SE stands for Spectrum Expert. This is also referred to as SOMM, but basically it's monitor mode AP, but analyzing the spectrum. This is a clean air AP that's configured as a connected sensor into the network. As a network sensor, it's going to gather information on the signal strength, the duty cycle of all RF transmissions within the bands that are utilized by the wireless network. That raw spectrum information, the data that we're collecting, that's going to be forwarded to analysis for any workstation running a channel analyzer with clean air. Cisco has their own application called Cisco Spectrum Expert. So it allows you as a customer to monitor that network, and it eliminates the need to have a spectrum analyzer, right? And spectrum analyzers can be tens of thousands of dollars. So the fact that this is built into the architecture is a beautiful thing. SE Connect devices can monitor the entire 2.4 gigahertz spectrum, as well as the 5 gigahertz spectrum at the same time. But when you're in this mode, as suspected, I mean, as you guys could imagine, you cannot support wireless clients, and it still consumes one AP license or one AP connection on your wireless LAN controller. Remember, wireless LAN controllers are licensed based on the number of APs that they support. So you obviously want to be careful with that, being that you may not have enough licensing to support this feature. Okay. I've used this primarily to kind of mess around. It's not something that you typically would use on a regular basis. You would most likely use this if you run into a situation where you have to do some advanced troubleshooting, right? There's just some crazy things happening in your spectrum, and you haven't had any success figuring out what that interferer is, and you're trying to kind of locate it and maybe even trying to identify what it is, okay? So it's not something you would be permanently running on the network. You can enter the SE Connect mode, select the drop down from the menu under the AP, apply it, wait for the AP to rejoin. After it reboots, it rejoins the controller. When the AP is reconnected, you select the AP. There's a key that you have to copy. I don't want to do it here because I'm using the wireless that I'm actually using to communicate with you guys on. But there's actually a key. It's called an NSI key that you copy from the AP configuration screen. And that's what you enter into your Cisco Spectrum Expert software package. Cisco Spectrum Expert is a free application. You don't actually have to pay for it. I used to have it installed on this machine, but I don't think I do anymore. But you can find it just about anywhere online. It's a free application. The only way that you can utilize it, though, is if you have a controller and you have a clean air access point. It has to be a clean air access point. Okay? An AP that's operating in local mode can pass raw RF spectrum information on the channel it's assigned to for analysis. But unlike SE Connect mode, it supports client access as well. SE Connect mode does not service clients. On the flip side, SE Connect will not have any impact on the overall processing of clients' data, right? So we're not trying to share the resources by doing the analysis. You know, local mode AP, passing raw radio frequency spectrum information, does still have the ability to service clients, but you kind of limit your view of the spectrum to the bandpass of the channel that the AP is assigned to. Meaning that we're only kind of analyzing a small portion of that overall spectrum. Okay? It also uses the same NSI key, but the key is available from the AP Details tab under the General tab. In fact, let me show you. I think that one I can show you because, let's see, General tab, AP Details. Let's see, AP Details. Where the heck did they put that? Let's see. Am I missing it? Oh, there we go. It's right in front of my face. There's the key that I would use, the network spectrum interface key. So I could actually place this. I could download Cisco Spectrum Expert, connect to the network, put this key in, and I can start to see some radio frequency data. Let me see if I can show you Spectrum Expert, at least visually what it looks like. Let's go over here. And you can get an idea. It's a really cool tool, actually, because it gives you a lot of detailed information about the spectrum, right? So you can see all these pictures here. You can see these are the three channels, 1, 6, and 11, and you can see that there is a high duty cycle interferer here, and you can use a whole bunch of different views to see signal to noise ratios, RSSI, and so on. So it's a very, very powerful tool to be able to analyze your radio frequency spectrum. And we're not talking about 802.11 traffic. We're talking about all kinds of RF traffic in that radio frequency spectrum. Okay? All right. Let me pause here real quick. So that concludes that lesson. We talked about a lot of stuff in this lesson, right? We talked about how APs can use 4 different modes to be able to discover their controller, broadcast, or locally stored information or primed information. Option 43, or DNS, using the Cisco-CapWAP DNS entry. We also have Flex Connect mode, talked about that, Office Extend mode, and what that provides. Then we also talked about the other modes of operation, like monitor mode and rogue detector mode and sniffer mode and bridged mode and SE Connect and so on. Hopefully, I know it's a lot of information, but hopefully as you go through this video and you guys listen to what I was saying and maybe go back and review it a little bit later on, at least when you're looking at the configuration and you're clicking that drop down, you'll have a general idea of what each of these modes represent. So it's no longer it's no longer difficult to kind of figure out what the heck you're looking at. Obviously, there's a lot of stuff we still have to cover with regard to all these different modes of operation. We were just kind of introducing the concepts in this particular lesson. But there will be other lessons that we get into that go into more detail on these particular modes of operation. So we'll wrap up this lesson. In the next lesson, we're going to get into exploring some of the additional features like client link technology and so on in the wireless LAN controller.